Hello everyone, my name is Tae-young Kim and I will be presenting our work on how to suppress strongly entangled concept in diffusion models using a delta vector. When you ask a diffusion model for a photo of Charlie Chaplin, it generates an image that matches the prompt. What's interesting here is that the generated image almost always features his mustache, even without any specific mention of it in the prompt. This seems like a natural result, as his mustache is an iconic element of him and his work. So let's consider a situation where you want an image of him without mustache. To be specific, if we input the prompt a photo of Charlie Chaplin and request the suppression of a mustache, the diffusion model should be capable of generating a photo of Charlie Chaplin while inhibiting the creation of his mustache. Let's define this problem more formally. First, the words in your prompt are tuned into the embedding vector. The core issue is that some words are strongly entangled with certain visual concepts. For example, the word Charlie Chaplin is tied to the image of a mustache in the embedding space. These connections are very difficult to break or suppress in the generation process. This is exactly the problem what we want to solve. Previous methods struggle with this issue. Some try to adjust the model's guidance, change the model's attention, or even try to impaint parts of the image. However, they often fail because they don't directly target the embedding of the main keyword, which has already become entangled with unintended information. As a result, even when trying to suppress the mustache concept, the activation remains and the unintended content still appears in the final image. So, our solution is to tackle this problem head-on. Our key idea is to edit the text embedding directly before it gets to the cross-attention part of the model. We directly modify the Charlie Chaplin embedding to remove the mustache semantic. By doing this, the model successfully generates an image without the mustache, solving the entanglement problem at its source. Let's see how this works technically with Steve Jobs' glasses example. Our method works by defining a delta vector. You can think of this vector as a directional vector representing the pure concept of what you want to remove, like glasses. We can take the embedding for Steve Jobs and subtract this glasses vector from it. When this new modified embedding is projected into the image space, the features for glasses are suppressed, all in a simple zero-shot way. But simply subtracting a vector can be a blunt tool and might damage other unrelated parts of the image. So we propose a more precise method called selective suppression with delta vector, which works inside the cross-attention mechanism. It's a two-step process. First, in the key pathway, we add the delta vector. This essentially tells the model, look for the areas where the glasses would normally be. This creates a highly accurate attention map that pinpoints the target region. Then, in the value pathway, we subtract the delta vector. We subtract the delta vector. This effectively removes the glasses information, but only in the specific regions we just identified. These two pathway approach allow us to precisely suppress a target concept while preserving the rest of the image. And we apply this to replication tokens, enabling precise spatial suppression using softmax. We also extend our method with an optimization-based approach. This is crucial for personalized models like DreamBoost, where subject features can be deeply embedded. To find a more precise delta vector, we optimize it using two key laws. First, a reconstruction laws on the inverted latent ensure the subject's core identity is preserved. Second, an attention loss use a simple mask to guide the delta vector, making sure it focuses on the exact region of the unintended content. This allows for far more accurate suppression. To evaluate our method, we built a new benchmark of strongly entangled concept pairs. Then we tested against baselines, including negative prompts, prompt to prompt, and instant paint. As a metric, we use cliff score, detection score, inverted FID, and human user studies. Across both standard stable diffusion and personalized Dreamboost models, our method achieves state-of-the-art suppression, delivering spread suppression, delivering strongly fidelity, and earning the highest human preference scores. Visually, the results are even clearer. You can see here that baseline method either fail to remove the unintended content or they damage the subject's identity and the background. In contrast, our approach removes only the unintended content like the light from the candle or the buttons from a shirt, while perfectly preserving the original image. This holds even in Dreamboost settings such as suppressing berries from the bowl. Our method also shows impressive generality. It works on difficult cases involving people, and by simply reversing the sign of vector, we can also use it to add new content with the same level of control. Finally, our approach goes beyond just objects. We can suppress abstract concepts like artistic styles, such as removing the Vincent van Gogh style, while preserving the underlying scene structure. This demonstrates that our method generalized from object to abstract concepts, making it powerful, broadly applicable tool. To summarize, we have identified the crucial issue of strong entanglement in the text-to-image models. Our proposed solution, the delta vector, allows for direct manipulation of text embeddings to precisely suppress or even add specific concept without degrading image quality. Thank you for your attention.